Now let's continue to look at one example. So given this series, sine 1 over 1 plus sine 2 over 4 plus sine 3 over 9, etc. And, the question is, if this series is convergent or divergent. And for here, this 1, 2, 3 is in terms of radians, okay? As we can see from this series, on the numerator here, it's sine 1, 2, 3, 4, 5, 6. Because sine of x is a periodic, and it's bounded between -1 to 1. So we can see that this series of the sine gonna have some alternating. Okay, it might not a fully, plus minus situation, but we can tell that they're gonna have sign change along this series. Okay, so what should we do? Well, first of all, we want to find the general expression for our an so that I can write this series into a sigma notation. It turns out it's not that difficult because you can see this is 1, right? This is 2, this is 3. So on the top, it's going to be sine of n. On the bottom is 1, 4, and 9. So we know that it's going to be 1 square, 2 square, and 3 square, etc. So our an here, so the series is going to be sine n over n squared. So that's easy. And now I would like to know that, okay, how do we check whether this series converge or diverge? Okay, we just learned the absolute convergent test and also direct comparison test. And then we can give a try, to both of them. So as you can see, if we can prove a series is absolutely convergent, then for sure the series converges. Okay, so following that, we know that we put an absolute value of this. It turns out the denominator is n squared. It is positive. So this absolute value sign only acts on the numerator, which is sine of n. And we also know that sine of n is bounded between -1 and 1. So the absolute value of sine of n is less or equal than 1 for all the n. Okay, so from this inequality, we actually can get that, okay, this series actually is less or equal than 1 over n squared. Okay, because if we block this part, as you can see that it's exactly absolute value of sine n is less or equal than 1, which is shown here. And look at what we have here. This series is a p-series with p equals 2. So for a p-series, when p is greater than 1, the series converges. So from here, as you can see that we can prove based on the direct comparison test that since this p-series converges, then this series converges. And from this series, this is absolute series for my original series. So that proves that my series is absolutely convergent. And hence, my series converges for sure. Okay? So just to want to let you know, the flowchart here is from here, we got this, right? It's just to put an absolute value to here. And based on the own property about the sine function, we construct this inequality. So for this inequality, we use the direct comparison test. Since this is a p-series, p equals 2, this is converge. And from here to here, we see that this is the absolute series for my series here. So since my absolute series is convergent, so my series is absolutely convergent. And for sure, hence, it is converge. Okay, so, and then this is the p-series, right? The format is 1 over n to the power of p. So the p-series converges when p is greater than 1 and diverges when p is less or equal than 1. Okay, So hope you enjoyed this video, and thank you for the watching.